It's time for us to do a brief review of some pre-calculus concepts, and perhaps you looked at this in Algebra 2. That's the idea of exponentials and logarithms. So we've talked a lot about different kinds of functions, but we haven't yet considered something like f of x equals a to the x power. And these are simply exponential functions. Some things to recall about these things. Like the graphs, as the exponents get larger, tend to explode. Right? Y equals, this could be a picture of y equals 2 to the x, or 3 to the x, or whatever you want to the x power, just depending on what the base is. In all of the cases, though, this would be a situation where a, the base number, has to be greater than 1. And you could have another kind of graph, exponential graph, that looks something like this. This could be y equals 1/2 to the x. It could be 1/4 to the x, depending on the scale. But all exponential graphs where a is between 0 and 1 will look something like this. And recall that this is an example of something that's decay, right? It's decreasing in value over time. And this is an example of something that's growth. Notice also that all of these simpler forms of exponential all pass through the point 0, 1. Notice that the domain of all of these is all real numbers, because any number can be an exponent. Notice that the range for all of these is that y must be greater than 0. Right, so all of that matters. Now, one thing to recall too is if we're solving equations of this type, you need to remember this fact that something to the x power, if it's found to be equal to the same base to the y power, then it must be true that the exponents have to be equal. So we can take that one fact and look at problems like this. 2 to the x plus 1 power equals 8. We need to solve for x. Well, it's true that 8 can be written as 2 cubed. So what must be true is that x plus 1 has to equal 3, which means that x has to equal 2. And we can use that fact in a lot of different situations. Let's look at a few more like this. Let's consider 4 to the power of 5x minus 1 equals the cube root of 32. Now I can't solve this offhand, but I can see that 4 is 2 squared, and that whole thing would be to the power of 5x minus 1. And 32 is 2 to the 5th, and that whole thing would be to the 1/3 power. And then using exponent rules that we should have mastered, both of these are examples of power to a power, so I can multiply the exponents to end up with 2 to the 5/3. And since the bases are now the same, the exponents have to be equal, so that when I go ahead and solve for x, that'll be what, 11/3, and divide everything by 10. I'll find that x is 11/30. Right, so that's a principle in solving these kinds of equations that we just need to remember. Another principle that you need to remember is how to convert quickly between exponential and logarithmic form. You know, different teachers teach this different ways, and I'm not going to make comments about other methods of doing things, but I'm just going to focus on the way that I like to approach it and the way that I teach my students. So if you've had me, this should be a review here. If you haven't, this is a different way if you haven't seen it this before. So exponential form, we'll say that it's y equals b to the x, where b is the base and x is the exponent. And I can convert anything I want to logarithmic form. I just have to remember in a lot of ways what the language is. So in this case, b is the base. So in logarithmic form, b will also be the base. The next thing I need to remember is that x is the exponent, and my exponential form and a logarithm always equals an exponent. And finally, y ends up being the argument of the statement. So if I know all these things, I can quickly convert from exponential form to logarithmic form and vice versa, just by knowing the relationships between these things. And some of you may have been taught another way to go about it. I would just submit that the way you're doing it is just involving more steps than are necessary, although it can be helpful to keep track of things. So if we use this idea here, let me start with some logarithmic things, like log base 2 of 8. I know that the answer is 3, but if I can't tell what the answer is, I could just rewrite this into exponential form. Right? 2 to what power equals 8? Well, I know that it's 3, and that's why this expression equals 3. Something that might be a little more difficult to see could be something like 5 times log base 6 of 1. Well, I know that 6 to the power of 0 equals 1, so that log base 6 of 1 equals 0, and this just becomes 5. Again, the question that I answered with this is 6 to what power equals 1? Well, it has to be equal to 0. And notice that at any time, if the argument is 1, then it doesn't matter what the base is, the logarithm has to be equal to 0. Finally, if we saw something like log base 7 of 0, well, there isn't any power that we can put 7 to get 0. This is simply undefined. And this highlights a bigger fact. 0 in this case is the argument. The argument of a logarithm must be greater than 0. Right? You'll always get a positive number, even if they're going to be really small. Now, some things that are important is to remember as well have to do with the base. If I just write log of x, that's equivalent to log base 10 of x. Right? Implied in both of these statements is that the base number is 10. And that's true in terms of AP. There are textbooks that do some different things, but at least in our context, this is the criteria that we're going to be using. So given that fact, let's evaluate log of 100. This just means 10 to what power is 100, and that has to equal 2. Right, if I saw log of 1, well, 10 to what power is 1? That has to be 0. Right? So those are all a variety of different things. Now, one thing to just make mention of is if you were to consider this expression, y equals 1 plus 1 over x to the x. Right, this is just a very curious function, and one thing to notice is that the limit of this function as x goes to infinity of the 1 plus 1 over x to the x, it's not 1 like you might suspect if you haven't seen this before, but it actually ends up being, it's exactly e. By definition, e is a number that's associated with a limit of this function, right? And recall that e is about 2.718. Well, that's important to recall because this number comes up a lot, specifically in terms of anything that has to do with natural processes and natural growth. So e being a natural base, we say e to the x equals 10. And something to recognize about this is that in logarithm form, this is log base e of 10 equals x, and we have special notation whenever the base of a logarithm is e. We can also write that as ln of 10 equals x. These ln of 10 and log base e are equivalent ways of saying the same thing. It just gets its own notation. Now notice that since in y equals e to the x, since e is greater than 1, the graph is going to look something like that, which means the domain of this function is all real numbers for x, and the range of this function is y would be greater than 0. some other things to consider in terms of e. Just some things to pay attention to. What is the natural log of e to the fourth? Well, one property to recall is that if you have an argument that's to an exponent, then it's true that you can rewrite this as the exponent, drop the exponent down. This would be 4 times the natural log of e. The natural log of e then just means e to what power is e, which is 1. So this just ends up being 4. Let's evaluate 9 to the natural log of 1. We'll recall the argument is 1. So e to what power is 1? Well, it has to be 0. So this ends up being 0. 8 times the natural log of the square root of e. Well, I know that square root of e is the same as e to the 1/2. If I drop the 1/2 down, this is 4 times the natural log of e. The natural log of e is just 1, so this is 4. Right, there's all sorts of different things to think about. Finally, in line with these, e to the natural log of 5. Well, this is just 5, and there's a few different ways to think about it. The way I think about it is this expression, natural log of 5, is an expression for an exponent. And it's an exponent that, if I were to write natural log of 5 in exponential form, it would be e to what power is 5. Right? So the natural log of 5 is the value of x. Right? So this is e to the x equals 5. This is just a property to pay attention to. The last thing is, let me remind you of 3 other properties involving logarithms. That if you have a logarithm and the argument can be thought of as the product of 2 things, then that's equivalent to the sum of log A plus log B. Another way of thinking about the same property is if you're adding 2 logarithms and the bases are the same, then you can multiply the arguments. Second property relates to these things in terms of division. If you're subtracting and the bases are the same, then you can divide the arguments. And we've already reviewed the other property, that log of a to the b power is the same as dropping the exponent out front, b times the log of a. And these should have already been proved to you in pre-calculus and perhaps in Algebra 2 if your teacher was on the ball. So just a few problems applying those properties, and then we'll be done with our brief review. What is log of 25 plus log of 4? Well, both these logarithms have the same base, 10, so I can multiply the arguments. This becomes log of 100. 10 to what power is 100? And it is 2. So this is another expression for 2. A different problem, log base 2 of 40 minus log base 2 of 5. In this case, again, the bases are the same and I'm subtracting, so I can divide the arguments. So this will be log base 2 of 8. 2 to what power is 8, and that's 3. Next, let's consider log of 10 to the 35th power. Well, I can bring that out front, so this is log 35 times log of 10. Log of 10 just means 10 to what power is 10? Well, that's 1. So 35 times 1 is just 35. And finally, let's solve a logarithm equation. Log base 4 of x plus log base 4 of x plus 12 equals 3. We're going to solve this for x. On the left hand side we're adding, and the bases are the same, so we can multiply the arguments. This is log base 4 of x squared plus 12x. I need to solve this for x, and one thing I can do is I can convert this to exponential form. This is the same thing as 4 cubed equals x squared plus 12x, which which is great. 4 cubed is 64. And now it's just a quadratic that we should be able to solve relatively easily. Let's see, 8 times 8, 16 times 4. So this should be minus 64. Let's not make a silly mistake here. So this would be x plus 16 times x minus 4. My only possible solutions are negative 16 and positive 4, but I can't use negative 16 because it'll cause the original argument of the problem to be negative, and that can't be true, so my only answer is x equals 4. So that's a brief review of exponentials and logarithms, and you'll do some more practice with that in your homework. Exponentials and logarithms, you just have to be comfortable with them and fluid with them in terms of calculus. It has to be a non-issue for you.